Hello and good evening, everyone. My name is Bill Miller, and on behalf of the Conejo Open Space Foundation, I want to welcome you to tonight's presentation, our second webinar of the 2024 speaker series titled Trail Geology, a look at rock formations, faults, and landscapes in the Conejo Open Space with Dr. Thom Davis. We're all thrilled that you are joining us tonight for this exciting and interesting look at the area's geology. I'm sure many of you are familiar with our work, but some of you may be new to our organization. As an all-volunteer nonprofit group, the Conejo Open Space Foundation focuses on educating our local community, the Conejo Valley, about our outdoor spaces. We also focus on raising funds to support programs and initiatives related to keeping those areas protected and accessible. Each year, we host this speaker series to help bring interesting and informative information to all of you on topics related to our beautiful Conejo Valley. As an example of one of the many ways that we make a difference, I'd like to share with you that in June of this year, COSF provided $10,000 to our partners at the Conejo Open Space Conservation Agency, further leveraging funding that they received for the Arroyo Conejo Trash Cleanup Project. This project removed more than 13 tons of trash and waste from the upper Arroyo Canal, and we are so happy to be able to support projects like these. Looking to the future, you can expect to see COSF and COSCA deepening our partnership, ensuring that our open spaces remain beautiful and accessible for decades to come. As the Foundation's president, I'd like to take this opportunity to also especially thank the many donors joining us tonight. Whether you contributed because of this event or are an annual donor, your contributions are truly making an impact in the work we do, and we thank you for making a difference in your community. Please continue to keep the Conejo Open Space Foundation in your philanthropic plans and reach out to us at any time. It's almost time to move on to our wonderful program tonight, but before we do, I'd like to share a few housekeeping items. First, note that all attendees are muted for the duration of the presentation. The presentation will be roughly 45 minutes, and there will be an opportunity for questions afterwards. We welcome your questions submitted at any time during the presentation with the Q&A tool at the bottom of your screen. The chat function has been completely disabled. So if you have a question, please use the Q&A button. As Ann is on holiday, I will be joining Steve in moderating the Q&A for us this evening. We will also be recording the event, so you can rewatch or share with your friends. It takes us about a week to get that up on our website, but we will certainly let you know when that's up and ready. As mentioned, Dr. Thom Davis is our presenter tonight, so a little bit of information about him. Thom Davis, PhD, is a California State Registered Geologist, number 4171, founder and director of the nonprofit Geologic Maps Foundation, Incorporated. He is owner of Thomas L. Davis, PhD Geologist, a researcher, geologic map maker, and author of geologic publications. Davis's work and research interests are in energy supply, structural geology, mapping, oil and gas exploration plus existing fields, natural gas storage fields, and active faulting and earthquakes. He has worked in and published on the geology, tectonics, and oil and gas sectors in California and Nevada, Bangladesh, Pakistan, Myanmar, Sri Lanka, Colombia, Venezuela, and Mexico. In addition to all this, you can find him on the trails either hiking several times per week or as a volunteer instructor and hike leader for the Geo Hikes and the Weekday Trailblazers hiking clubs. So, without further ado, Dr. Davis, please take it away.
Bill, thanks for the nice introduction. I assume all of you can hear me okay? So just let me know if there's some problems with this. And again, thanks to, well, not just Bill and Steve too, for setting this up and giving me the opportunity to talk about the local geology. So what I've done with, rather than give an academic talk on the Santa Monica Mountains, which is, kind of where all of the Conejo open space trails are, I figured I'd just emphasize what you see on the trail, give you a little more of a feeling that you were out there in the field with me or on a hike, and what you might see along the trail. So I've kind of broken it up into the various trail areas, and we'll run through that, and hopefully you'll get a kind of a good idea of what you're encountering. A lot of you hike a lot. A lot of this stuff will be familiar as far as the trails, at least. And so maybe this knowledge that I can impart will make you think a little more about, what you're walking across and what you're viewing. Okay, so the starting slide here is I've got a view up on top of Conejo Mountain. It's in the evening, and we're looking offshore. We're across the Oxnard Plain. We can see the Anacapa and Santa Cruz Island on the right. And, all of the area here is part of the Western Transverse Ranges. And I'll explain that a little bit later. But, we're definitely part of a geologic province that's sort of unique in North America, and because of its orientation, its east-west orientation. And we can get into that a little bit. Again, some of the things I want to get across to you is I consider there's three factors that really influence what you're seeing and encountering when you're hiking out here. And let's see, I'll go to the next. And this will start with kind of our setting a little bit. You can see this map here is a satellite false image terrain map. I think the original source is NOAA. And I've got these big red arrows on there, and they're in a kind of the north-south direction. So that's to represent the convergence that's going on in the upper crust today in the what's labeled WTR, or the Western Transverse Ranges. And we're part of that, as I mentioned. Let's get my little cursor to move around here. The Conejo open space over here, the COSF is, in the western Santa Monica Mountains, pretty much that area. And the Santa Monica Mountains line up pretty much with Santa Cruz, Santa Rosa, and then San Miguel Islands, and also Anacapa. And we know from the structure of the rocks beneath the ocean floor, it's actually one continuous sort of folded chain that continues on out and goes along the north edge of the LA Basin. Some of the other things you can note just about our area, we got the San Andreas Fault shows very nicely. Here's a kind of a groove across the landscape. Got another big fault called the Garlock Fault. And then Central Transverse Ranges, which is actually the San Gabriel Mountains to most people. And you can see this east-west orientation to the ridges and the mountains, and it's a result of this convergence where everything is being compressed in a north-south direction and folding up and compressing, building the ranges. And then if the image went further to the northwest, you'd see the Southern Coast Ranges, and you get more of a northwest orientation up there. And that's also mirrored down here in the Peninsula Ranges, where you get more of a northwest orientation, which is more typical of California. The other thing just note about this nice image is it's showing the bathymetry, that is the shape of the bottom, below the ocean surface. And the light blue is pretty shallow marine stuff, it's shelf, and then the deeper blues are the deep basins. That's the part of the Santa Rosa, Santa Cruz Basin there. And there's this basin out here, deep basin off. So, all of this is called the continental borderland, and it's a whole story, of course, in itself. But one thing you can see here is that these shelf areas, these shallow areas, and I mean shallow, it's probably less than about several hundred feet of water. It extends out to like in here, my cursor's sort of following it. And I'll talk about this in a little bit, but that represents more or less where sea level was about 20,000 years ago. And that will have one of the influences I'll talk about. So what I tried to do here is get across to you the important activities that have happened in the last maybe 30 million years that really what you will see in the field out here. Okay, so one of the things is the Conejo open space. Most of the land is where there's quite a bit of middle Miocene volcanic activity. Okay, so middle Miocene, in this case would be about 13 to 17 million years ago. And then I explained a little bit in the previous slide about that we got this crustal convergence that's going on now, this north-south crustal convergence, uplifting the transverse ranges. And that started about 3 or 4 million years ago. And of course, if you've been in Southern California any length of time, you've witnessed some of the effect of that. That would be the Northridge earthquake in 1994. That was on a compressional fault. If you go back to, if you were around in 1971, the Sylmar earthquake, that was a Whittier Narrows earthquake in 1987. We've had several events that, you know, they're not on the San Andreas, but they're closer to home. And, you know, they're quite, some of them have been quite destructive. And of course, they go into urban areas. So in many ways, it's considered at least an equal threat as the San Andreas as far as damage to society. The other thing that is we have to keep in mind about this area is climate change. And you know, there's quite a bit of discussion today about, you know, CO2 emissions and fossil fuel use, but there's an impact of climate change that goes back, you know, 2.5 million years or so that we need to take account. It's actually impacted the coastal areas quite a bit, and the Conejo open space land is close enough to the shoreline or to the sea level changes that go along with climate change, that they've had an impact. So the photos I'm showing down below, the one on the kind of upper left there, that's taken from around, it's in Sycamore Canyon by the ranger's house that's midway down the canyon. And it shows the Boney Range in the background. And you know, it's a lot of that is airfall that's come from a volcanic eruption, again, from about 13 to 17 million years. And so those big cliffs and outcrops that are up there, there are a lot of what we call ash and fall. They're not lava flows themselves, although there are some. Most of it is ash, and a lot of it is also these pyroclastic flows, which come off the side of the volcano. And one of the things I want to emphasize about what you see, the rocks you see, the volcanic rocks you see in the Conejo open space, is a lot of them are volcanic, but they're really best described as the volcaniclastic. They're things that they're due to processes off the flanks of the volcano. They're made, volcaniclastic means a sedimentary rock, but it's largely or completely made of volcanic material. And there's quite a bit of stuff that goes on along the edge of a volcanic belt that is actually not so much directly volcanic. It comes from the reworking and the blast deposits and all the stuff that goes along with building a volcanic chain. Okay, so jumping over back to that crustal uplift and Western Transverse Range development. This is a cross section. It's actually, the location is closer to Ventura. This would be the area of the Conejo open space, but it kind of illustrates. It goes all the way across the Western Transverse Ranges, at least from the coast, all the way over to the San Joaquin Valley. And here's the San Andreas Fault. And what are all these lines that I'm showing on here? Well, it's been about 30 years ago, Jay Namson and I published a series of papers on trying to reconstruct what the transverse ranges look like, the Western Transverse Ranges at depth. And this is one of our models. But you could pull this thing apart, and it shows that there's about, on the order of about 53 kilometers, 54 kilometers of shortening that had happened the last 2 or 3 million years. And as a result of that shortening, so the shortening, we're looking kind of just straight west. So the crust is actually being pushed together from both sides. And as a result of that, you get folding because the crust is trying to shorten. You also get these big faults that we call thrust faults or reverse faults, where the rocks actually, this piece used to fit down here. And these are the kind of faults that create earthquakes like the Northridge earthquake or the Sylmar earthquake. And so that's what's underneath it. And a lot of the stuff does not reach the surface. It's even under the Santa Monica Mountains. Something roughly similar to this is going on. And then we have it deforming up the San Andreas Fault here. That's a whole story in itself. And then we used a lot of well data. That's what these little triangles are. We think deep well data construct this picture plus surface geology. So what is actually going on here? What's causing this? Well, we think what's causing it is there's some incipient subduction. That's where one plate goes under another one. So we think the kind of relic Pacific plate is being subducted starting to subduct under the North American plate. And as a result of it going down, it shortens the upper crust. This upper crust is too light to go down. It's made of very light material. I mean, it doesn't sound like rocks should be light, but these rocks are lighter than the rocks in the Pacific plate. So they just won't go down. And so as this thing kind of closes up, goes down, it shortens the rocks above it that won't go down. That's its only response. And then to show you what we're talking about here, this will all be North America, the western edge of North America. Here's the modern day plate boundary. That's San Andreas Fault. And then the stippled pattern on here are the western transverse ranges, central transverse ranges, and then on in the eastern transverse ranges. So this is where all the shortening that we express here is taking place, including the islands, the Northern Channel Islands. Okay, so this is all getting uplifted, eroded. It all started, maybe 3-4 million years ago at the most. And this bigger picture here, just to give you a little more feeling on the setting, here we are in California along the San Andreas Fault boundary, but that plate boundary for North America changes up in the Cascade area. This is the Cascadia subduction zone. Here we have a plate, an oceanic plate being subducted under North America, and it makes the Cascade range. The Pacific plate or the relic plate here is partially melting and producing the Cascade volcanoes. And then that boundary, we have the strike slip San Andreas Fault boundary, but then it goes down to the Salton Trough and it becomes a spreading ridge between mainland Mexico and Baja California that's being rifted off. So all this stuff is being transported northward over time. We are on a little slice of what used to be North America here, and we're headed up to the north toward the Gulf of Alaska. And now that's part of that continental portion is now part of the Pacific plate. So the boundary's been moving around. Anyway, that's the main thing to get out of here. We're in a very active area since we're so close to a plate boundary or within a plate boundary, at least on a kind of a global scale. I don't want to spend a whole lot of time on this, but just so you understand when I'm talking about faults a little bit, this is a strike slip fault. So this one's left lateral, it's like the Garlock fault. So if you're standing on this block and you're looking at the other block over geologic time, this block would be moving to the left. Now, San Andreas is a right lateral fault, so the motion would be exactly opposite. In the transverse ranges, I mentioned that we had these reverse faults, or sometimes called thrust faults if they have a real low angle. And there, as you shorten the crust, you bring one block over another. I mean, that's the response it has to getting shortened. Either folds, faults, or some combination of that. And then we're not going to get into this. I do a lot of work out towards Nevada and Utah. And, there we have normal faults in the basin range. And that's a result of crustal extension. And then if the fault's below angle, we call it a detachment fault. But both of these, the detachment fault and normal fault, they're a result of extension. Okay. And then I mentioned before that we have we've been influenced heavily by sea level changes, variations. We're in a glacial period. We're in the interglacial right now, but starting about 2.6 million years ago, we entered a prolonged series of glacial and interglacial periods. This diagram on the left here, it shows you the sea level. There's modern sea level up here, and then it shows you the curve is basically based from ice cores and foraminifera, and they basically can reconstruct what sea level was doing, or in this case, back 300,000 years ago. Okay, so here we are today. We're in this interglacial. And then only have to go back, I mean, geologically, a very short period of time. And sea level's down 120 meters below where it is today. This has an impact on the coast. And it's not just the shoreline moving around. It impacts inland, and I'll show you that in a minute. Now, that's the rest of going into like the interglacial here. Then we have, this is a time very much like today. If we go out to Santa Rosa or Santa Cruz Island, we see evidence of this stage, what's called 5E. And then, it's periodic. It just goes back and forth. Generally the interglacials are anywhere from 60 to 100,000 years. And then the glacial periods are real sharp. Look at each one of these sea level rises, very quick. They're all like that. So when the ice age sets in, basically the ice, like, excuse me, let me back off. When the ice age ends, it ends very radically, and we get a rapid rise in sea level. Okay, and this is a lot of work that I've done is out on Santa Rosa and Santa Cruz Island, and it shows you a reconstruction of where we think the shoreline was for this relic island called Santa Rosa, which is today if you combine the 4 islands together, it's only about 25% of the landmass that's above water today as of that island. So it was a very large island, had a lot of impact on, the ecology and various things here. And you can see here, look at down here, this would be 25 to 20,000 years ago. The Ka means thousands of years. So that's really recent geologically. And that would have been the last big glacial period. Okay. And so the sea levels come back up very quickly here. And of course, when it's down, it has a major impact on the rivers and such. This kind of shows you what I'm talking about here. This just shows you the last 20 or so thousand years, and this sea level rise, it's worldwide. So it's stabilized pretty much in the last maybe 6,000 years. But if you go back before about 8 down to about 15, man, sea level was coming up quickly. That's because this big glacial period at 20,000, 18,000 years, that it, once it started melting, sea level came up very quickly. And what it does, it means when you look at the landscape or the bathymetry here, that shoreline used to be basically about here where I'm tracing with my cursor. It used to be out here. And you can see these are old valleys, incisions that result when sea level was here and the drainages were coming out here. So shoreline was out here and it was cutting, incising into these valleys. And we see the impact here. This would be the more or less the Conejo open space area. Okay, so what I'm gonna do real quick here is jump through the different trail areas and show you what you see on the trails, keeping those 3 factors in mind, that you've got the climate change, I'll show you more of that, how it impacts it, and then you've got the volcanic activity back at 13 to 17 million years ago. And then you have the uplift of the transverse ranges. All of these are playing an important role in here. And so we'll go to Dos Vientos and Conejo Canyons and Wellwood, jump down to Los Robles, and then jump over to Lang Ranch. Lang Ranch is a little bit different than the other areas geologically. This is a map, geologic map of the Camarillo and Newbury Park thing. It was made by this guy, Thom, very famous geologist. You can go to the Santa Barbara Museum of Natural History, and there's a whole section on Thom and his work. One thing I want you to note here is all this pink here is the volcanics, the Conejo volcanics. This is at 13 to 17 million years. There's Newbury Park, 101 freeway, and it's all striking, means the orientation of the rocks is more or less to the northwest, and then it's or northeast, excuse me, and it's dipping off to the northwest. So we can, essentially what you do is when you're out here, you can just walk through the whole section because all the layers are all dipping in one direction off towards Camarillo. And this shows you the hike up, the route up Conejo Mountain. There's Conejo Mountain. It's a dacite plug. Okay, so what I mean by dacite, well, dacite falls in this category. In what we do in field geology is we extrusive volcanic rocks, ones that have been cooled on the surface. We try to figure out how much quartz is in there, how much plagioclase, how much orthoclase. Anyway, we define something based on these percentages. And that plug, which I'll explain in a second, that makes the center of the island. That's a dacite plug. And so as you hike up through here, you go through some more andesite type rocks down in the lower part. As you cross the road there and you go through here, some pretty dark rocks. And then as you get up on this part, you see it becomes much more gray, light colored. You're essentially in dacite, but you're not in flows. You're in basically breccia, stuff that has been reworked. And then eventually you get into the core of the mountain, which is the core of the old volcano. This was not a volcano itself. The shape of it today is not representing what was going on 13 to 17 million years ago. But you do have the kind of center sort of isolated, but it's changed quite a bit in the last 13 million years. So this shows you another picture of it. That's the hike up the Conejo Mountain. So the surrounding mountain has this dacitic breccias. Okay, there's a dacite, very light colored. And then you start out down here in more basaltic rock. And this is a common sequence that you see, especially in areas where you're near an oceanic plate, like we are, the Pacific plate, or within one, that you get volcanic material coming out, or magma coming up, and it gets contaminated by the crust, by the continental crust, and becomes more quartz rich and lighter colored over time. So you evolve from the andesitic basalt to a dacite basalt. And excuse me, this just shows a geologic compass. Had a student taking an orientation of what the rock layers are doing. So these rocks are layered around the edges, and these breccias, they still have sort of what we call bedding or stratum layering. And these little symbols here, these looks like little compressed T's. They represent the strike, and then that's the dip. And that's the dip is the amount of inclination off the horizontal. So they're all dipping to the, basically to the northwest here. And then you get into the plug itself, and it's more homogeneous. Now this shows you, this is a nice diagram that Dibley has on his map. And basically when you go up Conejo Mountain, you're walking through this stuff here. You're walking from these breccias like an apron around this plug. So this plug is the core, or at least a feeder, of what was one of the major, volcanoes of the area. And then I define, if you don't know what a breccia is, it's really coarse grained rock with a lot of angular fragments. And here's an example here. Now this is on that hike up to Conejo Mountain. When you get up the side of the mountain where the power poles are, if you look at the gray rocks, you look closer and you see that it's made of all these little broken angular pieces of other rock in there. Okay, so this is probably a blast deposit, or at least some kind of submarine debris flow off the flank of the volcano. And this is, again, one of the things I want to emphasize about the volcanics in this area, is that a lot of them are sedimentary in origin. I mean, they're made up mostly of stuff that is volcanic, but they've been reworked. They've had something. They're not flows themselves, although there are some flows in here. And then deeper down here, I'll talk about this in a minute, the Topanga Formation is the underlying, it's a deep water sedimentary unit. Conejo volcanics are very thick here, up to 9,000 feet, and they're 17 to 14 million years. We got a lot of age dates on the Conejo volcanics. And this shows you kind of just a cartoon illustration of what I'm talking about here. Here we got the core of volcano. That's the core of Conejo Mountain. That'd be that dacite plug. And then the flanks are all these various debris things that are going on. You can have pyroclastic flows, you can have submarine avalanches, and you get a very high sedimentation rate when you've got volcanic activity. So what you see in the rock record is you see what's preserved is the stuff when a lot of activity was going on. And then there'd be long periods where nothing was going on. And then things get reworked and you've got, just the regular sedimentation out of the water column going on. I'm jumping over now to the area that up there in the Western Plateau area, and it shows you you can take this hike that starts at the TO Service Center and goes around, and it basically is in that same sequence. Conejo volcanics here is very thick. You start out in some basalt flows down low, and then you go into these andesitic breccias. Again, a lot of the stuff here is sedimentary, and it's really a breccia, although it's almost all volcanic material. There's an example there of what it looks like in the field. And there's a basalt, very dark colored rock. So jumping back over to climate change, how does this influence, way back into the Conejo open space? Well, here's a Google Earth image of the Western Plateau area. This is Conejo, Arroyo Conejo. There's the service center, TO, and another part of the Western Plateau. If you've hiked out there, there's these big flattish sort of stretches, that are being carved up now by these deep canyons. And here's, Hawk Canyon. And, if you hike down this thing, especially when you come back out, you appreciate how deep these canyons are and what, how much they've cut into this older, what we call older landscape here. And this blue line I put on here is what was happening to represent the drainage from the Arroyo Conejo out to the coastline. And that exists today. But back at 20,000 years ago, when the sea level was out here, then this thing was carving down. And all the stuff that you see here, we think, is a result of, it may not be the last big sea level drop, it may represent several, but we think these big steep canyons are a result of sea level changes, and impacted the drainage. Of course, went out through the Santa Rosa Valley and around, but we think once you start dropping sea level, 400 feet, it has dramatic effect on erosion. This shows you a little better picture of what it looks like. There's these flattish areas. Here's the road that goes down, the trail that goes down into Hawk Canyon. You got some older alluvial deposits, but you got these flattish surface, the Western Plateau, that's being carved up by these steep canyons. So we think sea level changes, especially sea level at 20 to 30,000 years ago, was producing a lot of erosion back up into these mountains. And this would be an example of what I'm talking about here. So this is a low sea level stand, cartoon of that. And then you'd have this incised valley cutting in here. And then it leaves along the shelf edge an imprint of these canyons. Jumping over to the Wildwood Park area. Here I'm showing, it's more or less the Santa Rosa Trail and various things that come around here. And you're going through the same kind of Conejo volcanics. And one of the interesting things over here, though, is you start seeing some pillow lavas. This is a pillow lava, and a picture of one. And pillow lavas are where you have submarine flows, and they cool when the flow, the magma is actually coming out on the ocean floor, and it cools. This is kind of a cartoon of one, and it produces these kind of round globe sort of shaped things on the bottom, and they're very distinctive in the field. So we know when we see these that we're dealing with submarine volcanics here. Again, this is the trail over at it's that Los Padres Trail, and then going out further. And one of the reasons I want to put this up, it's, you can't see it with this little thing up here, but it follows more or less how the basin is changing. On this side, we're dealing with the map here, the northwest strike of the or northeast strike, excuse me, of the Conejo volcanics. Okay. And then when you get over to here, you start picking up all these other units and they're cutting across, and you got these, what I call unconformity here, and you're changing the basin. You're really going from this basin over here into another basin on the other side. It's got different units. They're younger and they set depositionally, on top of this. And there's a little bit of erosion that went on at that time. Here's a picture of that breccia. That most of this area is this andesite dacite breccia. The Lang Ranch area I wanted to jump over to next. This is Dibley's other map that I used to make a lot of this. A lot of those maps I'm showing you are, I take Dibley's maps and I put them in the GIS into ArcMap, and that's kind of what we do today. Anyway, you can see that there's quite a color contrast in here. Here you've got this is all this Miocene rocks, last maybe 14, 15 million years. That's all goes out towards the west. And then you've got this older, blue and green showing up here. And these are much older rocks. And this is a cross section showing, it's a north-south cross section. So, Simi Valley is over here. Here's Westlake Village. And you get your Conejo volcanics folded up in here. But, generally it's kind of a south dip and then rolling around. And there's one of your dacite plugs. But then these rocks here dip in completely the opposite direction and much older. And they're older by a good 40, 50 million years. And they have this strong north dip here. So you head from upper Cretaceous into lower tertiary rocks going that way. And when you're hiking, let me show you the next. This shows you that Dibley map, the Thousand Oaks map I just showed you, but it's all been put into our map. And this is the trail that goes up to Simi Peak. And it's all on this green Cretaceous task course formation. It's a marine formation, deep water. It formed at the time, at the very tail end of the Cretaceous, so the last days of the dinosaurs. And then you've got this, your Oak Brook Vista Trail. That one, that's kind of interesting from a geologic standpoint because it'll follow this that you see, this contact here. And so when you follow it, you're kind of hiking. At one point you're in the older basin, and then another point you're in this younger basin, and you're right at the contact between the two of them. And so what is the significance of this stuff back here, all this older rock? Well, this is a picture of, along that Oak Brook Vista, looking at some Cretaceous sandstones. And this is the map of what it looked like back in the mid-Eocene, so about 40, 50 million years ago. And offshore was, the whole setting was much different than today. We had a oceanic plate out here called the Farallon Plate that was being subducted under North America. I don't know if you can make out, but there's a boundary, there's a coastline of California putting on there. And there's Baja California down in here, and a little harder to see Nevada and Arizona here, but we're basically out in here. And this is a cross-section showing you what was going on at the time. So you had this Farallon plate descending under North America, and then you had this big forearc sequence, which is called a forearc. It's a big sedimentary basin that, they're linear and they parallel your volcanic arcs. We see these worldwide, and that was also right here. So what we're looking at is a remnant of that, the little broken up pieces of that all over the place, a lot of it up in the Great Valley area of the San Joaquin Valley, Sacramento Valley. But we've got a little remnant down here that is preserved along the Lang Ranch and Oak Brook Vista. One other thing I wanted to show real quick, it's kind of off the Conejo open space land, but it shows you this is the going down Sycamore Canyon, up the Fossil Trail, around the Boney, and then down Blue Canyon and around. And I've got two faults here showing. There's, I wanted to say a little bit about faulting that reaches the surface. There's not much right in the Conejo open space land as far as surface stuff, but these are two big faults that are nearby. And you can see, so here's all the pinks and reds, that's all Conejo volcanics, it's all Conejo volcanics. And then you got these older rocks, the Topanga Formation caught in between. So there's this block essentially been uplifted. This is brought up this side relative to that. We know just by the stratigraphy because these are older rocks. And the same goes here. These rocks have been uplifted relative to the Conejo volcanics here. And so when you hike these trails, you basically follow this fault pretty well. And then of course, when you go back up Sycamore Canyon, if you go that, kind of route, you'll follow this other Sycamore Canyon fault here. I think I have a little, let's see, let me just, I might have skipped something here. Oh, my little thing is on the top. Say, Bill? I don't know if you can.
Dr. Thom.
Yeah, do you want to try to run that video or do we have time for it?
Let's keep rolling. Let's keep rolling, please.
Okay.
We will attach your video to the recording.
Okay. I have a YouTube channel that has a bunch of these things where I just shoot them in the field and they're not very long. We'll worry about that next or some other time. So this just shows you Sycamore Canyon and that's Newberry Park up there, and it shows the other south end of the, what I call the Western Plateau, this flattish area that Newberry Park is basically parts of Thousand Oaks are built on. There's a little closer view. That's that same hike trail that, goes along down Blue Canyon up Sycamore Canyon. And you may have, if you've hiked this, certainly coming out, you thought, oh my gosh, coming out of this thing, it's 600-700 feet of climb out of that thing. And why is it so steep there? Why is it so flat up here? And then, you just go down in this sharp canyon. Well, we think it's the result of when sea level was out here 20,000 years ago. And remember, that's pretty recent geologically. There's Sycamore Canyon. So when sea level was out here, it was 400 feet lower. It was carving up this area. And the thing about this stuff, it happens so quickly in geologic terms. The drainage never has time to really equalize, or it's always in a state of erosion, high erosion, and when sea level is so low, Now, of course, it's flooded back and it's not cutting down as much, but that steep gradient you see when you come down into Sycamore Canyon, we think that's a result of this very active erosion that was going on when sea level was much lower. Just if you hike the fossil trail, you've probably seen the fossils. There's quite a reef there. They're not in place. It's Pecten magnolia. And so in the old days of geology, this was a type fossil for the Topanga Formation. It's a beautiful fossil. And unfortunately, some people have banged on it now and then, but there's, the reef continues on into the bushes where people fortunately don't seem to go and bother it. Real quick. So what I showed you is the Conejo open space land, kind of along this red vertical line. Mostly the western part is Conejo volcanics. And then over at Lang Ranch, you get into this older section here. And the diagram here is kind of an east-west diagram, just to show you that the variation in the Santa Monica Mountains go all the way from, the Hollywood area all the way across, Encino area and then Thousand Oaks and through here. So again, you're kind of in this area as far as rock units for most of the Conejo open space land. And then at Lang Ranch, you do get this, you see something older and more interesting there. Just to kind of put this back into summary. So the rocks we're seeing, largely Middle Miocene volcanic rocks. A lot of, there are flows, but most of it's volcaniclastic, rework stuff. And then, of course, we're in the Western Transverse Ranges, and we've had this crustal convergence started about 3 or 4 million years ago. It's producing our local earthquakes and uplift and the mountains and the erosion. And then we've got climate change superimposed on that. Started about 2.6 million years ago, the interglacials and glacial periods. And the landscape, especially within, I'd say, 10 or 15 miles of the coastline, is responding to that because of the very radical changes in sea level. Once you drop your base level for your streams, 400 feet, it's going to have an impact that goes inland for some distance. And so this just basically, again, your volcanic activity, your western transverse ranges here and here, and then your climate change situation. I think that's it. Yep. So that's my concluding statement on the Conejo open space land and the geology. I hope that helps you a little bit, and it wasn't too confusing.
Dr. Davis, amazing. Thank you very much. I am just thoroughly engaged with your presentation, and I think many of our viewers were. So I just have to say, it's great to have some clarity and understanding on the geology in our area. Your presentation will certainly change my experience in our open spaces for sure. So thank you for dedicating your time to help educate us not only about the geologic history of the area, but some of the interesting sites that we can see while we're out on the trails. So at this point, we'd love to hear from the audience. So it's time to hear from all of you. We do have some questions in queue, so we'll get started with those if you're ready.
Okay. Yep. Yeah. Thank you too. You're welcome. I mean, enjoy it.
Fascinating. So thank you very much. All right. So Stevie B is asking, hi, Thom. Since the geology of the nearest Channel Islands is the same or similar to the mainland, why wasn't Santa Rosa connected to the mainland?
It was pretty close. I think maybe it got as close as 5 kilometers, 3 miles, at more or less where Anacapa and Point Mugu, or a little bit to the west of that, came together. It was close enough. We're pretty sure where a mammoth, a Colombian mammoth, the big one, was able to get out there to the islands and then eventually get isolated and become a pygmy mammoth. So there just wasn't enough. It could have been. We don't know much about the history prior to about. We've got a pretty good record of the interglacial. We're in an interglacial, sea levels higher. There's one from 80 to 130,000 years ago that we got a decent record of. But beyond that, we know from worldwide records, there's all these other interglacials. We don't have a very good record of that stuff, So it could have been connected, I mean, the island could have evolved through several phases, being an island, not an island, an island again,
It could be shallow, right? Could be shallow waters.
Awesome. Yeah.
Okay, thank you very much. Kay Isaacs asks, what was the mechanism for sea level change influencing the canyons here?
Okay, so Sycamore is pretty obvious what happened there, because it goes directly out to the sea, and we have a pretty good idea of where sea level was, 20,000 years ago. So it was 400 feet below. I mean, and that, Sycamore Canyon isn't that long of a drainage. So, to drop something 400 feet is going to change what we call the base level. And so what will happen is the river system, the drainage, will try to, it will erode until it reaches some kind of stable position. And these things were happening so quickly in the geologic terms, they probably never reached any sort of stabilization. So that's why you have that big escarpment up there at the top of Sycamore Canyon. When you come off of, when you're hiking that area south of Windy and Potrero, or that big flattish spot, and it just drops off. So when you see that in geology, it indicates to a geologist that something radically changed. It's and it doesn't appear like that thing is so active today. So there was something in the past that it changed.
Okay, great, thank you. There were 2 earlier questions that were related. both Gary and Jay Spurgeon, I think I'm pronouncing that correctly. The questions were, where were the actual volcanoes, and where was the main volcano that influenced our Conejo Valley geology?
Okay, so it's very difficult to say because it's the rocks have been. I mean, okay, one thing that I always try to get across to students in geology when they first the land, especially in a place like California, coastal California, because of all the tectonics and various things going on, the landscape that we see today does not. It may look a little bit like what I've been arguing about. You know, may have some record of the last couple 100,000 years, but that's about it. I mean, after that, and so if we go back to 13 million years ago or 17, the landscape looked completely different. I mean, just completely. We probably weren't near the coastline to begin with. We were probably at least, I'd say tens of kilometers from any sort of continental coastline. And the rocks have been, since then, they've been uplifted, they've been folded, faulted. And so the actual, in some places like Conejo Mountain, we see this big, what we call dacite plug, which is the core of a volcano. It may have just been a feeder. I mean, it could have been even larger. We don't know where a lot of the other ones are because they can be covered up by younger sediments. So we don't have a very good picture of that, quite frankly.
Yeah.
The main thing to keep in mind is that it looked so different back then,
Well, we do sit on the ring of fire, right?
Yeah.
So there is that. Christine Elowit asks or says, I'm interested in the intersection of geology and biology.
Mm-hmm.
Are you familiar with how these various rock types impact the plants that tend to grow on them? For example, some parts of the Conejo open space area have a lot of cacti, others have none. Interestingly, the hotter, drier parts of the Conejo, for example, the areas of budding Oak Park and Simi, lack cactus, while the hills overlooking the coastal plain have many.
Yeah. There is, I mean, there's an influence. I can't say I have much experience other than what I've seen myself in the field in the botany and the geology. One thing to keep in mind is there's another science in between, and that's soils. And I have been out with soils people before. And there's the rocks play an important, the chemistry of the rocks play an important role. But the kind of the where they are on the slope, how well drained it is, different plants seem to behave, respond differently to those kind of things. And I mean, worked a lot on Santa Cruz Island, and I'm always curious about where there's cacti on Santa Cruz Island, which it doesn't make much sense to me why it's where it is. And the same goes for pine trees. You have both of them on Santa Cruz Island, and I think it has to do more with kind of the micro weather than just about anything. That makes sense.
Yeah, I think so. I mean, it totally makes sense that the rock, of course, would play a part. The chemistry of the rock would play a part in the soil, but there's a lot of other things in the soil as well that impact that, and the weather and the drain, to your point, the drainage. So thank you.
Yeah. We have one formation. I mean, it's not so much, we have a little bit in Santa Monica's, but it's the Monterey. You may have heard of that. Very silicious in places. It's a result of diatom blooms, and that, the rock can be nearly almost close to 100% silicious material. Plants don't like that stuff.
Yeah.
So when you have that, then and of course plants generally like the volcanic material, especially if it's more mafic or the stuff that has a lot of iron and magnesium. I mean, that's kind of a general rule,
Speaks to the Santa Rosa Valley a little bit.
Yeah.
All the egg down there. Anyhow, moving on. Gary K6 GPS asks, any comments on the recent Malibu Topanga quakes?
Oh, yeah, you guys asked me about that earlier. I haven't gone and looked at it much. I mean, it sounded like from the little I read that it was on the Malibu Coast Fault or something related to that. Sometimes we still do, like there was an earthquake down in Highland Park, in kind of northeast LA. We got involved in that. If we have data that we can kind of pull up and look at and compare with what the seismologists are saying, then yeah, sometimes we'll jump into it a little bit. Those two earthquakes, so I think there were two of them. I haven't got involved in those, at all, And,
This is one that's related, and it just came in while we're on the topic. It's from Kathy Bailey. I am also interested in the impact of the recent quake activity. How long until movement is measured and confirmed?
well, you mean, okay, there's a couple different ways that, I mean, now we have satellite instrumentation. It's very, very precise. It's, pretty much, all the time. And that can tell you a lot. I mean, that can tell you a lot very quickly about what's going on. If, sometimes people will still, in big quakes, they'll go out and put an array of instruments out and try to measure, any kind of ground movement, stuff like that. And that might follow with the aftershocks, get a better idea of, what they're dealing with at depth. I mean, really today, especially with the United States Geological Survey, the USGS, their sites, they have a couple of earthquake sites that they're very quick, and it's not just the U.S. They can tell you a lot about what's going on, some earthquake in Central Asia or something, very, very quickly, as far as I would say that if you're interested in a movement, like how much has moved, how much mountain went up, or how much fault moved, that can be determined pretty quickly today.
Okay, great. Technology is amazing.
Yeah.
It really is. Joan says, thank you, Thom. So I would agree. I'm going to echo that so much.
You're welcome. Hi, Joan.
We still have a few more here. People who are genuinely engaged with this, and it's terrific. Nate Undercuffler asks, are the crystalline basement rocks beneath Conejo open space related to the crystalline rocks that comprise the San Gabriel Mountains where they're at the surface?
Ooh, good question. Well, we don't have any, I mean, if you're talking about the closest, what I would call metamorphic crystalline, kind of depends on how you define crystalline basement, but actually, I think what Nate's referring to, the closest thing that we would have in the Santa Monica Mountains is way to the east over there, essentially where the 405 freeway is, the Santa Monica slate or schist. And then further east, of course, you get into the San Gabriel Mountains. The closest basement we have going to the north, crystalline basement, north of us, would be up in the Fraser Mount Pinus area. They're not related, those two things. What we know about we're kind of guessing is what's below the Conejo area, as far as that deep in the section. It's just not exposed. Now, Santa Cruz Island has a schist on it that in some ways somewhat resembles the stuff over there in the eastern Santa Monica Mountains. But it's really speculation as to what's down there, And
continuing, we got two more right now. So Tom Becker asks, and if it's it's Tom Becker, I know he's one of our board members. How do you think the Coba Arch was formed?
The Coba Arch.
COBA is how he put it.
I don't know what that is.
If he's still
I think that's the one just to the west of Simi Peak.
Just to the west of Simi. Oh, you mean those little holes in the rock? Is that what you mean? Like that? Is that what the Coba Arch is?
Yeah, you can stand in them.
Yeah, right. Yeah, those. Okay, so that Eocene sandstone is, or not Eocene, that's Cretaceous there. Let's see, what's the age of that one? Yeah, it's Cretaceous. That, it has a lot of the porosity permeability, that's kind of like the void space in the rock. And then the cementation in those rocks, it really varies quite a bit, just over a very short area. So you have these pockets that wear out when the rock gets near the surface. Some areas undergo weathering very quickly and start producing these pockets. Other areas are very resistant because they've got silica or calcium cement and they last. So over time, you might have one area that just erode through completely due to weathering. I mean, I don't think it's anything else other than that. I mean, it could be a little bit of wind action, but I think it's mostly just, weathering, chemical weathering over time, and mechanical weathering. There might be a little, freeze now and then or something but it's really the soft parts of the rock going out. They're not real caves in the true sense of like a limestone cave or something, a dissolution cave or something. Yeah.
Cool. Awesome. Related to that, and I don't know if anyone here can answer it. Maybe you can, Dr. Davis. The Cova Arch is a misnomer. Who named that? What is its origin? I personally have never heard of it. You haven't either. So we're just
no. But that, there are a lot of local names, so people.
Yeah. Thought it's. I use the trails and every most people that I see on the trails, if they're hikers, they call them one thing, mountain bikers another thing. It's the same thing. Okay, so Mel Duke asks or says, please discuss, and this could be a big one, please discuss the intersection between volcanic activity, geologic formations, and the oil gas formations near Ventura, Ojai, Santa Paula, etc.
Well, there's not, okay. The volcanic activity, back 13, 17 million years ago. So it's much older than the oil and gas that has basically formed in the Ventura Basin oil fields and things like that. That's all. It's an active generation, what we call a pod. I mean, the rocks that sourced it, they're younger than the volcanic rocks. There's this Monterey again, and for the most part, they're younger, and they didn't start being buried deep enough or cooking up enough to generate hydrocarbons until probably the last 2 or 3 million years. So there's a big time difference between those two. The volcanic activity doesn't really, I mean, you might think that the heat from the volcano would cook up some source rocks. That's been observed in other places, but actually, we don't think that's going on here. What was the other question there? What was the other part of that thing about?
It was the intersection between the volcanic activity, geologic formations, and the gas formations in the Ventura County area.
Yeah, I don't think there's much. Let's put it that way, association. Although there is this weird little thing that makes no sense, but there's this little, if you drive down the Conejo grade and you get down there, what is that thing at the bottom, the springs, Camarillo Springs, is that the name of that little community down there?
Correct. Yes.
Yeah, they used to be an oil field. I mean, a long time ago, it's been long. I mean, that area's had some mudslides and fires and a few other things, but before they put the houses in there, it was actually a little oil field. I have no idea how they figured that out. It must have been some oil seeps or something, but it all was abandoned, probably close to 100 years ago, but so the oil must have migrated in there from some other part of the Ventura Basin or something, but it is a little bit of oddity right there.
Okay. All right. So here's the deal. The questions keep coming in. It's getting late. We're going to do 4 more. We've got 4 in the queue right now, and then we'll wrap it up. Does that sound good to you?
Yeah, sounds good to me. Yeah.
Terrific. So we'll start. We're back to Nate Undercuffler, and he asked, do the Santa Ynez Mountains have a similar geologic story to the Santa Monica Mountains?
Well, rock-wise, they're much different. They're by and large older. They're more like those rocks that we see at Lang Ranch, those old that's really what it's those old fork rocks that are making up a lot of the rocks behind Santa Barbara and Ventura, Ojai. And what was the other part of that question?
Let me see. Go back here. I got it. Bear with me. Do they have a similar story to the Santa Monica Mountains? So
They would be okay. The uplift and convergence of the crust, of course, would be related to what's the north-south compression that I talked about earlier. That's due to something going on, deep within the crust, in the lower crust or even down in the upper mantle. Okay.
So the forces
have a commonality there. Yeah.
Yeah, the forces were the same, but the rock
formation. The rocks are different. Yeah, the rocks are different.
Yeah. Jeff Kerfess asks or says, I have seen circular rocks that when eroded look like a flower. There will be a lot of them in a sedimentary looking burial exposed in a road cut. What might these be?
Like a flower?
Yeah, think of Rose Valley Road. Those rocks that
almost like
they could be concretions, I guess, which is again, it's like a nodule that forms in the rocks, again, from preferential cementation. And could be something like that eroding out. I'm pretty much speculating right now without seeing something like that, Yeah.
Maybe Jeff, you could email president at COSF.org a picture of what you're talking about, and I'll be happy to share it and share it with Dr. Davis and follow up.
Sure.
All right. Craig Percy says, can you explain how tifonis are formed? There are tons of them in the Simi Hills. Tifonis being Tifonis.
Oh, I don't know what that is. You got me on that one. Never heard of it.
Well done, man. Feel free to email me again.
Yeah, that's another one. I'll have to look up that one.
I'll be happy to follow up with Dr.
I mean, there's a lot of oddball names in geology, but I have to say I don't know that one. Yeah.
Okay, and rounding it out for the evening, Greg asks, is Sandstone Peak, the highest point in the Santa Monica Mountains, really sedimentary or is it igneous?
Oh, that's a good question. That's a really good question because I don't know if that debate will ever end. Okay, so Sandstone Peak. When I've actually been up there a couple of times and thought about this because I heard from other people. Well, some claim it's volcanic, some claim it's sandstone. It's a lot of the mountain, a lot of that peak is a volcaniclastic rock. Okay, so when you look at it in the field, it does look like an igneous rock. But when you look really closely, you realize there's parts of it that it's just been reworked. It's volcanic material, but it's been reworked as a sandstone. So in other words, there's some bottom current or some process going on, as the flow was out there on the surface, it got eroded and then reworked down slope, into something else. But I've seen other stuff up there on other parts of it that looks like an andesite flow. So I think it's both up there going on. And I mean, that's a little bit of a chicken sort of statement. I mean, right at the stuff I've seen right at the peak, to me, looked like a sandstone, a volcaniclastic sandstone. So, I mean, it's 100% volcanic material, but it's been reworked, And I think that's where some of the confusion has come in, But there's a lot of that. I mean, that's really what Conejo volcanics are, by and large, is a lot of volcaniclastic stuff,
Yeah. As someone out on the trails and if having come off my bike on the trails a few times, I'm well aware of the volcanic nature of the rock.
Well, some of that stuff pretty rough,
Pretty sharp, yeah. So I will say, first of all, thank you. This has been fascinating, and I really appreciate your insight and everything that we've spoken about. And I also want to thank our audience. Thank you for sticking around for the Q&A. Thank you for the many thoughtful questions that we have. And many thanks to all of you, everybody that's participated in this event. Of course, again, Dr. Davis, thank you so much for leading our discussion tonight and sharing your many insights with us.
Oh, you're welcome. I enjoyed it. I mean, I'm glad the audience had so many questions. That shows that there was interest. I hope some of you out when you're out hiking and at least think about some of this stuff, when you're out hiking around. And thanks to you and Ann and to Steve for setting this up, really, really enjoyed it.
We're grateful to have you, and that's the best part. Like I said, it's going to completely change my experience in the outdoors. And geologic time is just mind-blowing when you think
Well,
about it.
yeah, it's like thinking about how far the stars are away. It's a little hard to comprehend.
So unfortunately, on that note, our event is now coming to an end. Like I said, I know I have a lot of takeaways from tonight. I hope our audience does as well. If nothing else, to the audience, I hope this webinar gave you an opportunity to stop and think about the natural beauty of the area, because that is what truly makes the Conejo Valley unique. And I think we all know that. To all the attendees tonight, I encourage you, please get out and enjoy the Conejo open spaces. The days are starting to cool down. The trails, I can tell you, are in great shape right now. And now is the perfect time to go see for yourself all of the features and the landscapes that Dr. Davis spoke about tonight. So enjoy our Conejo Valley. Please continue to be partners with us in the months to come. Thank you all for your donations, for your volunteerism, and for your participation in the open spaces. I'll see you out on the trails. Until next time, good night.
All right. Good night. Thanks.
Thanks, Dr. Davis. We'll see you soon.